So we covered quite a bit of work, quite a bit of material already. Mechanical energy, kinetic potential energy. What is work? The integral f dx. Did I push on the wall and ask the classic question? I'm pushing really hard on this wall now. How much work am I doing? Zero. There's no dx. There's no change in displacement. That should be one of those key concepts that you mastered a while ago, but I remember first time I saw that, it's like, what? That doesn't make sense. I'm pushing harder on the wall. I must be doing more work. Nope. Unless there's some displacement to go with it. Lifting a weight, rotating a shaft, electrical power, the integral of the power to get the amount of energy per unit time. So if you were given W dot and you wanted to calculate the work, you just integrate with respect to time. True? Yeah, go back and forth between the amount of a process from initial to final state and the rate, the power. We really got to integral P dV, so we have boundary work. And we talked about polytropic processes. Again, this class is sometimes hard because we have new terms. What does polytropic mean? Something fancy. It's just basically the pressure times the volume to an exponent on that volume, some power like N is equal to a constant. And I mentioned what those N's typically are. 0, 1, about 1.4. All right. Then we talked about 3 modes of heat transfer. Conduction, we had a rate equation for conduction. Is that on your equation sheet? The rate equation for convection, the rate equation for radiation, and how to use them in simple problems. And we really got to an energy balance for a closed system. All of this chapter is closed system. We really don't have any open system analysis. What's the difference between an open and a closed? Either mass flow across the boundary or no mass flow across the boundary. And we don't have mass flow across the boundary, so it's a closed system. So we want to be able to write down the first law of thermodynamics, which is basically an energy balance statement for a process. So we have the first law for a process would be something like this. We would say we could change the energy in a system. So E2 is the final amount of energy in the system. E1 is the initial amount of energy in the system. 1 is the start. 2 is the end. Those are the typical subscripts, 1 and 2. Initial state, final state. Start at 1, end at 2. So did you put more money in the bank? Did you put more energy in the system? How did that happen if energy is conserved? Well, you have to keep track of it. It could have come in the form of heat transfer during the process. That is typically an in. Q is our sign convention for Q is positive into the system. So if we write Q 1 to 2 is 10 kilojoules, that's 10 kilojoules of energy via heat transfer transferred into the system. And then why do we have that minus sign? Well, because it's the work during the process, and that work is traditional sign convention is out of the system. So if you had a work transfer, say 10 kilojoules of work transfer, it would be out. You say, this class doesn't look that easy or that hard. You know, that's true. I should say, this class doesn't look that hard, right? It's a simple equation. Well, we have, sometimes you'll write it as a delta E. Delta is just the change from initial to final. So final minus initial. And we think of 3 forms, macroscopic forms of energy. 2 you're very, very familiar with. One is the kinetic energy. The other is the gravitational potential energy. These 2 come from your prior background. How fast is it going? What's the mass of the system? Isn't the kinetic energy the 1/2 mv squared? V is the speed. What about the potential energy, PE? Isn't that mgz? How high is it in elevation? Maybe it changed elevation going from Z1 to Z2. Maybe it went down, lower. So Z's change. But the new one, maybe, is internal energy. And That's delta U. U is internal energy. Well, could we write it as a simple analytic expression like the kinetic and potential? No, not really. In special cases, we can do it. For a solid, knowing specific heat, temperature change, you got it. I can write that down, but that's only a special case. We talk about steam that's got some vapor and liquid in it, or an ideal gas. No, it's not that easy. We have to be more careful. We didn't get to chapter 3 yet, okay, where we talk about this substance. I can write the change in internal energy this way. But what you can think about is that it's roughly the mass of the system, some appropriate specific heat, and some temperature change. Well, or just put temperature minus reference temperature, such that if you put in here the change in internal energy, sometimes you can write it as MC U2 minus U1, or, whoops, I messed that up. The mass, specific internal energy change, or you could write it, if appropriate, mass times the specific heat times the final temperature minus initial temperature. I know that's not always true, but if you see the internal energy, think of changes in temperature. But it cannot just be changes in temperature, it could be changes in temperature and pressure. Okay. Where the kinetic energy, that's just mass, well, 1/2 mass, the final speed squared minus the initial speed squared, isn't it? Is it affected by pressure, temperature? No. No. And then the gravitational potential energy, mg Z2 minus Z1. What does this work? Well, this work 1 to 2 is a transfer of energy, and let me just say it's organized. Organized energy transfer. What do you mean organized? We'll talk more about it, but it's on a molecular level. If the shaft is rotating, all of the molecules in the shaft have the same rotation. You know, they're going around the same axis, the same rotational speed. Where if it's a heat transfer, Q1 to 2, it's because on the molecular level, some of the molecules are higher temperature, higher kinetic energy, higher rotational and translational and vibrational energy states at the molecular level, and they're colliding and bouncing and moving around, and that's kind of a disorganized energy transfer. That's really the difference between the two. I know it's hard to grasp. Maybe you say it's pretty easy to grasp, I think. You know, one is disorganized. Heat, you need a temperature difference, high, low temperature to move it. The other is you don't need a temperature difference, but you need some sort of organization, a shaft, moving energy across. So anyway, this requires hot and cold. Otherwise, you're not going to get the transfer. So it requires a delta T. That's it. That's our first law. It's an energy balance statement. You just need to keep track of. It's like bookkeeping. That's all this class is. A lot of engineering is bookkeeping. Can I keep track of all of the energy, the forms, and the transfers? Let's solve a problem. Gas in a piston cylinder assembly undergoes a constant pressure process, and the pressure is 300 kilopascals. So from an initial volume, they give us the initial volume, 0.6 cubic meters, to a final volume, 0.66 cubic meters. What happened? Was it compressed or expanded? Was it expansion or compression? It's expansion, right. While it's being heated. Okay. So right away you can see, oh, I have initial volume, final volume. Maybe state 1 for initial, state 2 for final. Maybe I put 1 initial, and maybe I redraw the diagram over here, and I'll call that state 2. And if it's expanded, do you think the piston went up a little bit? Sure, the piston went up a little bit. It's expanded. Okay. What's the focus of the study? Well, the gas that's trapped in this piston cylinder assembly. And if it's expanded, it's not expanded by pushing and making a larger diameter cylinder. No, it's pushing back the face of the piston, lifting the piston a little bit, the way we've shown it. All right. The change in the internal energy of the gas is 63 kilojoules. What information did they just give us? Did they just give us in that statement right there, that's 63 kilojoules? Did they give us that U2 minus U1 is equal to 63 kilojoules, or lowercase u2 minus lowercase u1 is 63 kilojoules? What did they give us? The first one, right. Now, somebody says, sometimes I see this cap U, sometimes I see the lowercase u. What's the difference? It's divided by mass. It's either the specific internal energy or just the internal energy. You can tell by the units. If they give you the units of kilojoules, that's cap U. If they give it kilojoules per kilogram, that's lowercase u, specific internal energy. The same thing for kinetic energy. Professor, sometimes I see they give me cap Ke, sometimes lowercase ke. What's the deal? Well, this one would be 1/2 mv squared. Guess what the lowercase ke is? 1/2 v squared. It's cap Ke divided by mass. It's specific kinetic energy, if you wanted to give it a long name. How about cap Pe? That's mgz. The lowercase pe. What is lowercase pe? Specific potential energy. It's just gz. That's it. All right. So this is the information that they gave. And I know when you're brand new to a topic, it takes time to assimilate. How many people have solved a few problems already in preparation for the exam? Yeah. How many people have spent 20, 30, 40, 50 minutes or more on one problem? All hands should go up if you're a regular person. Some student came up to me years ago, Professor, what's wrong with me? You solve the problems in 10 minutes. When I do it, it takes me an hour. I said, welcome. That was me when I was doing the same class. Took me an hour. I remember some statics problems. That took me forever. I would go in a loop, throw away the sheet of paper. I was lost. Try it again. Okay? So, if you are struggling and taking a long time to solve problems, that's normal. Now, I will share one thing, that we did not have the internet when I was in your shoes, which means I didn't have electronic access to the textbook or electronic access to the solution manual, which means I had no clue whether I was right or wrong when I'm solving problems, because I couldn't just go flipping through and find a solution manual. Don't get addicted to the solution manual. My recommendation is never look at it. Well, how am I going to know if I have the right answer or wrong answer? What happens when you graduate? You think they're going to give you textbook problems? The boss is going to pull out solution manual to the problem you just solved for 3 weeks? No, he's not. Or she's not, or they're not. So anyway, if you spend 5 minutes, you get frustrated, that's it. I'm going to the solution manual. You dug yourself a hole. Good luck, right? Have you experienced that yet? Stay away from the solution manual. All right, now let's get back to this problem. I'm going to try and solve it in less than an hour. The local atmospheric pressure is 100 kilopascal. That's the pressure up here on top of the piston. Okay. What is this 300 kilopascal? That's the pressure inside. That's P1, 300 kilopascal. Professor, is that gauge pressure or absolute pressure? P1, 300 kilopascal. Gauge or absolute? With confidence, or I'm going to have to guess on this one, it's a 50-50. In this class, for this type of problem, especially as you work through other problems and read the textbook, you'll find that when they specify a pressure like that, it's absolute. And it's very rarely gauge, very rarely. And they have to make it clear that, oh, this now is gauge pressure. Otherwise, it's absolute pressure. And you look in the steam tables, it's all absolute pressure. When you need the ideal gas equation, you need the pressure to go into that. It needs to be absolute. So basically, it's absolute. the whole way through. Somebody says, can you tell me what P1 gauge is? If the absolute pressure is 300, atmospheric pressure is 100, what's the gauge pressure? You got 50-50, right? Either I'm going to add 100 or subtract 100 from 300. And it's 200. But we don't need to do that, but we're reviewing a lot of material as we solve this problem. Part A, considering the gas as the system, calculate the work. And here's the answer, it's 18 kilojoules. And the heat transfer, and there's the answer, it's 81 kilojoules. Okay, how am I going to calculate the work? And then how am I going to calculate the heat transfer? First of all, what are they asking me to solve? Pick a symbol for what they're asking you to solve. The work, how about W? How about W1? How about W2? How about W1 to 2? How about W1 to 2? There's a lot of potential symbols to pick for it, what you're asked to solve for. But that's a thing it's worth struggling with. Okay? How many people say, that'd be okay? How many people say that'd be okay? How many people, these are the struggles you work with when you're solving these homework problems. True or false? Yeah, exactly. And then if you get off on the wrong track, I feel like I'm robbing you if I just tell you what's wrong and what's right. Because you need to discover this yourself. But I don't have time. This is wrong. Never write W1. Why? It's not a property. We can write T1, we can write P1, we can write V1. Those are properties. We could talk about values at that state 1. There is no work at state 1. It's a transfer. It's an interaction. Same thing there. No. You can leave it blank, saying, okay, I'm assuming it's for the process from 1 to 2. You could put 1 to 2. This is very, very standard for this textbook. And other textbooks separate it so it's not like work at 12. It's work at, beginning at 1 and going to 2. So it's like you have a pre-subscript and a post-subscript on W. Every now and then I'll write it that way because I prefer it, but it's not used in the textbook, so I'll try and avoid it. We're looking to calculate W1 to 2. What about for this part, Q1 to 2? We should know before we go after it, what are the units that I expect for my answer? SI units. I expect it in kilojoules. Okay. Now, how can I calculate W1 to 2? What's my strategy? What's my approach? I reread the problem. First time you reread the problem, 4 or 5 times. Professor, what's wrong with me? I have to reread every word in the problem statement 4 or 5 times before I understand what to do. Normal. So, how am I going to calculate the work 1 to 2? Think of that integral f dx, which in this class, PdV, for pushing back the piston away from it and expanding against that piston. That's a way to do it. Okay. How can I make this integral? You can make this integral night and day very easy if P can come outside the integral. When can P come outside the integral? When P is constant. I searched the wording of this problem. Is P constant during that process? There's my key word right there, constant pressure process. Whew. So, now I can write that the work 1 to 2 is the integral P dV. So that's my constant pressure, 300 kilopascal, times the final volume, because I'm going from V1 to V2. The final volume, maybe I should have wrote it down, V2 is 0.66 meter cubed. V1 is 0.6 meter cubed. So it's going to be 0.66 minus 0.60 meter cubed. Then I look for unit conversion. You must handle unit conversions very well. How many people already know how to get kilojoules out of this one? Yeah. A kilojoule is precisely 1 kilopascal times 1 cubic meter. So it cancels the kilopascal, the cubic meter. I'm left with the answer kilojoule. And I would write the answer as work 1 to 2 equal to 18 kilojoule with a box. How many equal signs in the box? How many significant digits are on the answer? 2, but sometimes the problems work out to 2 or 3 significant digits. Don't give 4, 5, 6, 7, 8, 9. I think usually every semester I get somebody gives me 9 significant digits for an answer, and it's like, I don't know if they don't know what they're doing or what. All right, what about Q1 to 2? Is there an integral h dt or something like that, or some integrand dt that works for this? There isn't. You were introduced to integral f dx in the physics class. You were introduced especially to f dx in the dynamics class, right? Well, we haven't exposed you in the curriculum to how to do a lot with heat transfer at a mechanistic level. There was the rate equation for conduction, the rate equation for convection, the rate equation for thermal radiation. Yes, they're introduced in this chapter, but they're kind of like window dressing. There's a whole class you take after fluids. It's called heat transfer. Whole 3-semester credit hour class devoted to beating you up conduction, convection, radiation. Is there any more to that class? Conduction, convection, radiation. I teach it, okay? I enjoy it. It's a great class, but it's just conduction, convection, radiation, rate equation. So once you would get Q dot, you could integrate dt, yeah, but that approach isn't going to work. It's like a similar, the analogy is this approach worked. What's the analogous approach to get Q? Change path. Try a different strategy. Don't go with the fundamental conduction, convection, radiation, rate equation and try and use it. You won't work here. So what do you have to use? Energy balance. Energy balance. So we write the first law for the process. We have that change in the energy is equal to Q in minus the work out. This change is a change in internal plus the change in kinetic plus the change in potential energy equal to Q1 to 2 minus work 1 to 2. Sometimes I do this. I know that. This is what I'm looking for. Change in potential and kinetic energy of the gas as the system. They didn't tell me I could neglect it, but guess what? You can neglect it. Is there a huge macroscopic motion? Is there some speed at which this whole cylinder is moving and then all of a sudden it slows down or speeds up from initial to final state? No. Is there a great change in the potential energy due to elevation? No. Somebody will struggle with this. They'll say, look, there's the center of mass, the centroid of that gas. And now, because it's expanded a little bit, isn't that gas centroid moved up a little bit? Sure. Pick some values and chase that one, and you'll find that it's way out there in the digits, way out there. It's negligible. So I know some people struggle with that. When can I assume it's negligible? Solve a lot of problems, get a lot of experience, and then you'll see. And the textbook does the same thing. So the kinetic and the potential energy are negligible, or there's no information to allow you to calculate it, so you leave it alone. And then this delta U, hey, that was given to me in the problem statement, wasn't it? Up there? So what is the answer? Q1 to 2 is equal to W1 to 2 plus delta U. Q1 to 2, it's 63 plus 18. Is that 81? And it's positive. What does that mean? It was truly heated. There was heat coming into it, transfers of energy via heat transfer into the gas. I hope I didn't take too long on that problem. Does it make sense? Part B, continuing the same problem. The piston is well insulated from the gas and moves without friction in the cylinder. Consider the piston as the system. Uh-oh. The piston as the system. Is it the piston in the gas as the system or the piston only as the system? It's only the piston as the system. Calculate now the work. The work? Huh? This one's tricky. This one's conceptually tricky. There's my system. It moved. I'm not redrawing the whole box, but there's the system now. When it was moving, tell me a little bit about the pressure beating down from the top and the pressure beating down on the top. Did the pressure beating down on the top change? What was the pressure always up there? 100 kilopascal. The pressure on the bottom, beating up, pushing up, and the pressure on the bottom, pushing up, pushing up, pushing up. Did it ever change during the constant pressure process? And what was the pressure there? 300 kilopascal. I know that the piston, it's kind of a weird statement, but this is thermodynamics, okay? And if you just follow the logic, it'll work itself out. So, if the piston is the surface and it's pushing back the atmospheric air, it's pushing away the atmospheric air. From the perspective of the piston as the system, it's doing work to push back the atmosphere. It's a work transfer out of the piston because it's pushing back the atmosphere. Make sense? But what about with respect to the gas below it? That's actually what's pushing on the piston to lift it. True? So what you're going to have is two work transfers. The work for the whole cycle for the piston as the system will be the work 1 to 2 boundary at the top plus the work for the process 1 to 2, the boundary work from the bottom. How does that notation make sense to you? Does you see what I'm struggling with? I got two work transfers. Okay. What about the work boundary at the top? It's pushing back. Is that going to be positive or negative? The first term. It's going to be positive. What about the second term? Positive or negative? From the perspective of the system, the gas is pushing it, and so it's negative. All right, now let's calculate each of these knowing that one's positive, one's negative. It would be the integral PdV. Hey, I've done that before. 100 kilopascals times the V2 minus the V1. Now, what you're doing is you're pushing back the volume of the gas, the air, and so that was 0.6. It'll be 0.06 meter cubed pushing back. That's how much the air pushed back. The piston pushed back the atmosphere. And then what do you have here? You have either you take care of the minus sign right there and put 300 kilopascal and then a positive 0.06 meter cubed, or you say, oh, that's a negative 0.06 meter cubed. Either way. And so what are you left with? You're going to be left with a negative 200 times 0.06 kilojoules. And that gives us negative 12 kilojoules, work 1 to 2. What does it mean it's doing negative? Well, it's actually receiving increasing energy by the work transfer from the gas below it than what it's putting out with the gas on top of it. What about the heat transfer? Well, it's well insulated. What does well insulated mean? No heat transfer. So by observation, that's 0 kilojoules, just reading the problem statement. Now, what is the change in the potential energy? Well, let's go to the first law. We'll say the change in total energy, which is the change in internal, plus the change in kinetic, plus the change in potential energy equal to heat transfer into the piston as a system during the process minus the net work out of the piston system. So we just said that this term is 0 because it's adiabatic. What about change in internal energy? There's no change in temperature. What about the change in kinetic energy? The speed's not changing. So the term, what I'm interested in calculating, the change in the potential energy, boils down to negative of the work 1 to 2. So the change in the potential energy ended up to be plus 12 kilojoules. Actually, the piston went to a higher elevation. How much higher? I mean, I don't know the mass of the piston. I don't know the the change in Z, but I know the change in the potential energy is positive 12 kilojoules. Yes?
For the 0.06 meters, is it squared or cubed?
The volume 2 minus the volume 1 is 0.66 meter cubed. Oh, did I not write this is a cubed.
Yeah, because the kilojoules.
Yeah.
You get it from me.
Yeah, it looks like a squared, but if I say squared, I made a mistake. It's cubed. Any other comments, questions? Let's go on. We can write energy balance in multiple different forms for the process. Can you write it for a process? Sure, we just did. So we have the change in the total energy, which you have 3 components to sum up to the total energy, is Q 1 to 2 minus work 1 to 2. What is a differential form? Very, very small change. So small, we don't use delta. What do? Small, little delta, little d. That's a differential change. And then we have a little heat transfer, delta Q, and a little work transfer. Professor, why don't we write dq minus dw? Why is this funny, delta there for in front of the q and the w and not a delta e,
Because they're non-property.
That's right. This is incorrect syntax-wise because it's a property, it's a d difference. This is incorrect here and incorrect there. So we want to emphasize that these are small interactions, not small changes in properties. How about a rate form? If I take this differential form and take every term and divide by a small change in time, what does this become? The time rate of change of the energy in the control volume is equal to the rate at which it's flowing in with heat minus the rate at which it's flowing out with work. So we have a rate form. So this is just as good. This is just as good for a process from initial to final state, and as a function of time, a rate equation for an energy balance. Make sense? An electric motor draws a current of 12 amps with a voltage of 120 volts. Maybe here's my rendition of electric motor. All right. And we have the I is the current, 12 amps. And a delta EMF, delta E is 120 volts. Sometimes it gets a little ridiculous. It's like a change in volts is equal to 120 volts. So you put a change in V is equal to 120 V. And it's like V in both sides. So it's like, that looks confusing. Let's change a change in the electromotive force, EMF, measured by volts, is equal to 120 volts across the legs, supplying electric power to the motor. The output shaft of the motor is a torque in it of 10.2 Newton meter and a rotational speed of 900 RPM. 900 RPM. What symbol do we want to use for rotational speed? N, omega, something. Different textbooks, different symbols. N is often used, or omega. Okay. You can convert that to so many radians per second. Can you not? All right. For the steady state operation, determine the motor electric power to the motor. Okay. Determine the electric power to the motor. Well, that would be some symbol E dot electric. How do I calculate the power to the motor? Isn't it just the change in the voltage across the lines leading to it times the current? And there's one other term. If you have a three-phase and it's alternating current, There's a term in there. It's not in our textbook, but how many people already took the EE class? You're supposed to get a lot out of, right? But I took an EE class like that too, and I didn't get a lot out of it. But when out there in the real world, there'll be a PF. Anybody know what a PF is? Power factor. And guess what? All the electrical engineers are too important playing with computers and computer engineering to know anything about power. And so an mechanical engineer, guess what? You're responsible for the electric motors and power and how they operate and how they work. And if you get into that line of work. So please, it's going to be really important for you to master the ability to do lifelong learning, because you're going to have to come up to speed quick. Did I tell you my son graduated mechanical just from Texas Tech just a couple weeks ago? And the company's sending him for like 9 months of training. Hold it, 4 years or 5 years to get your BS in mechanical. And yet your company has got to send you to 9 months of training. Make sure you come out of here with the ability to learn, because that's really more important than what you actually do learn. But anyway, power factor, tuck it away. It's really important. You have a shift between the phase, the voltage phase, and the current phase. They're not in sync. If you put the AC power to a resistor, power factor is 1. But when you put it to an induction motor, you get a large shift. That's why you have capacitors to help move that inductance back up to compensate for the inductance in the motor. But that was a digression. But this is what you want to do right here. So you calculate the power by the product of so many volts, so many amps. What about the unit conversion? What's a watt? Is it an amp times a volt? Who said Physics 2 was the hardest class they took? Isn't it an amp times a volt, the watt? All right. Yes, it is. You can put that on your equation sheet as well. All right. So what do we calculate? We 120 times 12. So you get 1440 watts, or 1.44 kilowatts. What symbol do you want to use for electric power? I don't know. Put E dot with the subscript ELEC. Something to be clear. This is my electric power being supplied to the motor. Where's that power going to go? Well, we want most of it to go out into shaft power. But it's a energy conversion device. That's what a motor is. It converts electric power to mechanical shaft power. What's the shaft power from the motor? Let's write it up here. W dot shaft, S-H-A-F-T, or just S-H. How do I calculate that? That's right. It's just the torque times the rotational speed. And you got to check your units. Let me just say, work your units on this. You'll come out with 0.943 kilowatts, W dot shaft. Now, so into the bank goes 1.44, out the other end, 0.943. Where's the rest go? Do an energy balance around this system. There's no mass transfer around the system, so it's still a closed system analysis. But you do have electric power. You have mechanical power, okay? And then what else is coming off? Q dot, heat. So it's operating at steady state. So if I wrote the rate of change of energy inside this system with respect to time is equal to the rate at which heat is being transferred in minus the rate heat is being transferred out plus the W dot electric in minus the W dot shaft out. See what I'm doing? I'm saying this is my electric power in. This is I'm subtracting a positive shaft work out. All right? So this is steady state. Do I really have an in? No, it's all out. So Q dot out of the system is W dot electric in minus W dot shaft out. So 1.44 minus the 9.43, and we find Q dot out is equal to 0.498 kilowatts. What is the efficiency of the motor? What do you mean efficiency of the motor? Well, it's the ratio of what you want out of the device over what you had to pay or provide to make it work. And so what do you want out of a motor? A large heat transfer? Nah, you want all that power to go in the shaft. So it'd be put it in symbols, W dot shaft. What do you have to provide to make the motor work? The electric, W dot electric, Q dot, not W. E dot electric. So this is 0.943 divided by 1.44. And if you have a calculator, you can calculate that percent. The efficiency of the electric motor, are there any units on that? Or is it dimensionless? Dimensionless, right. All right. Part D, what is the motor surface temperature if the ambient air is 25 degrees C and HA is 12 watts per Kelvin? What is A in this HA product? A. Area. What is the name of H in that HA product? Convection heat transfer coefficient. So they're giving you the convection heat. So you look up or you remember that you had a rate equation, Q dot convection is HA times the temperature surface minus the temperature of the fluid far away. Some delta T that drives that convection heat transfer. Hot motor, cool air surrounding it. So if I want to calculate the surface temperature, the motor surface temperature, that's what I want to calculate. It's equal to the temperature of the air around it plus Q dot convection, what is the rate of heat transfer that I have to dump into the room away from the motor, divided by the constant or coefficient H times A. And when you calculate it, you find that it's 25 C plus blah, blah, blah. This surface temperature comes in around 66 degrees C. You want to touch that? You want to touch that and hold your hand to it? Probably not. It's going to be warm, right? 66 degrees C. That all look good? Yes, sir.
For parts, part B where you have the work of the shaft.
Yes. Yeah, it's the torque times the rotational speed. Well, they gave it 900 RPM, and you just need to make sure it's in radians per second, and then convert units to make sure that you got that right answer. Yes?
What is the name of the symbol for efficiency?
It's eta. It's a Greek symbol, eta. Anybody else? Efficiencies. I know that the coach in football, they say, go give it 110% on the field. It makes no sense. Efficiencies, like 100% is best and then below, okay? So what you want is often a ratio of what makes it work and what you want out of the system. What you want out of the system divided by what you have to provide to make it work. Okay. Now, before we spend a lot of time on detailed analyses of cycles, we want to have a general power cycle. So this may seem a little odd, but here's a system. And when they put a box, that means it's a system, and then they put an arrow like this. What does that arrow indicate inside the box? Going in a cycle, going in a circle, doing it again, repetitively, again and again and again. When your automobile engine's running, it's running at 2,000 revolutions per minute, 3,000 revolutions per minute, and you're just cruising 3,000 RPM, right? You're not gunning it or anything. You're just driving down the interstate, going somewhere. And if you're cruising at 60 miles an hour, that engine will sit there and just purr at 3,000 RPM or whatever the speed is for that car, for that speed, right? Machinery just runs in cycles again and again and again and again and again. So that's what they're indicating. You're running in a cycle. You're just doing it again and again. So here for a power cycle, we often have to bring in some heat. let's say we bring in some heat here. Q comes into the system somewhere. For a power cycle, to generate power, you also have to throw some out. That's waste heat. We're going to find from the second law, there's no way that you could take all of Q in and convert it to what you want, which is the work net out of the cycle. But this is a very high-level illustration of a general power cycle. What do we want? We want to bring in Q. What type of units would this be? Kilojoules. Let's say somebody wrote Q dot. You could do it on a rate basis. Then it would be kilowatts. You want work out of the cycle, the net work out of the cycle. You want that to be large. You want that to be as large a fraction as Q in as possible, but you can't get it to be 100%. Because in a real heat engine, you have to throw some to the environment. You have to waste some heat. So we have the efficiency, the thermal efficiency of a heat engine is a ratio of what I desire. What do we want from a power cycle? A large net work out. What do we have to provide to make it work? We have to provide the heat in, not the heat out. That's a waste. It's just what you have to provide to make it work. So here is an efficiency of the cycle. And then they could play all kinds of games. Let's let, given this, given that, whatever, make some calculations. Let's see if I have a problem on the next page. For a general cycle with Q in, Q out, and W cycle, the heat transfer in is 60 kilojoules, and the heat transfer out is 30 kilojoules. What are they telling me? So organize it. So Q in is 60 kilojoules. Q out is 30 kilojoules. Here's my general cycle, system operating in a cycle. That's in, that's my out. So now, calculate the net work out of the cycle. W cycle. Well, you do an energy balance for the whole system, and all of the ins have to equal to the outs. It's just an energy balance. So Q in is an in, work of the cycle is an out, and Q out is an out, obviously. And so the work of the cycle is equal to Q in minus Q out, which is 60 minus 30. So it's equal to 30 kilojoules. Part B, what is the cycle thermal efficiency? Well, that's just what you desire. W cycle divided by Q in, and it's 50%. Makes sense? When we get to second law analysis and the Carnot efficiency, we'll get an analytic expression for the maximum cycle efficiency, and it depends on the temperature hot that you're bringing in Q in and the temperature low that you're throwing the heat away in, and the maximum is 1 minus TL over TH, and that equation looks too simple. But we have to work a lot to get to that equation. But it gives us an upper limit on the thermal efficiency of a heat engine. Again, what does most of thermodynamics? Burn something to turn something. So we already talked about a cycle, a power cycle. This is a general. Get good at sketching these things. Q in, Q out. This is the work of the cycle. But sometimes you have a cycle, something that operates, but you don't get power out or work out. You have to provide power or provide work. What would that be? A refrigeration cycle. So you put W into it, or W dot into it. Do you notice the change in the direction of the arrow? And then what does a refrigeration cycle do? You have a refrigerator. The refrigerator is sitting in a hot kitchen. There's some leak of heat into the refrigerator. If you lost power and the refrigerator was not working, even though it's a well-insulated refrigerator, after a few hours or days or weeks, what would be the temperature of the inside of the refrigerator? It would be the room temperature. It would get warm. So continuously running by drawing power from the electricity, you are taking through a mechanical system and pumping that heat that leaked in and throwing it back out. It's kind of leaking in the door. The kids open the door all the time, stand there, look for 20 minutes. How many people heard that? Shut the refrigerator door, right? You're just going to let all that heat in. And then when you shut the door, then it has to run more to pump it all out. So what leaks in has to be continuously thrown out. So what you're doing with the refrigeration cycle is there's a low temperature and you're always taking heat out of the low temperature, which is hard to do. And then where does that energy get dumped once you've taken it out of the inside of the refrigerator? Energy has to be conserved. Anybody have the fan blowing and you can stand there with your bare foot right in front of the refrigerator and feel the warm air blowing out? If you have one of those type where it exhausts in the front, how many know what I'm talking about? A couple. Some people, they know that it's just coils in the back. There's no fan, and it's just natural convection. Then they push it tight against the wall and they wonder why it doesn't work good. No, hold it back away from the wall so it has a nice chimney effect back there and it'll work better. Or it gets all clogged up with cobwebs and other dust and lint that it's like, how does it transfer heat?
What about the people that have a refrigerator in the garage?
It has to even dump it to a higher temperature in August. But it's a little easier in December because it's colder outside. So, yeah, really. But you have to dump this to Q out. Now, let's do an energy balance for this system. How many ins for a refrigeration cycle? 2. The work and the Q in. I don't put a dot on that, just put a Q. All right. How many outs? So right away, I can tell you this Q out has to be how much comes in plus all of the work of the cycle. That has to be dumped out. So from an energy balance, you can solve for Q out. Likewise, here's a heat pump. How many people know if they have been in a house with a heat pump, or their parents own a house with a heat pump, or the apartment has a heat pump, or they even know what a heat pump is? Residential heat pumps, right? So basically, most homes in San Antonio, if it's in the winter and you want a little heat, they just take electricity, dump it through a resistive heater, blow air across it, and that's your heating inside the house. But if you go further north, that would be super expensive because they have a much longer winter, and so they have a lot of heat pumps. We have some in Texas, but as you go north more, you'll get many more heat pump systems in the homes. And what that is a refrigerator or air conditioning system run backwards. So what they're doing is they have a cold, let's put this one, different ways of writing it. Let's do it this way. I'll do it still this way. Let me do it that way. You still have to supply work to it. Typically it's shaft to run a compressor, shaft power to run a compressor, but that's a work to provide it. And you take heat out of something that's cold. What? Yeah, heat out of something that's cold. You mean the cold outside on a cold winter day, you're going to make it even colder outside so you can get some heat out of that cold air that's outside, yep, and then contribute that and dump it into the house. And from an energy balance, Q out, this is really going to the inside of your house. This is the cold outside, right? And that's still the Q in plus work of the cycle. So a heat pump cycle is just like a refrigeration cycle. Well, then what's the difference? When I compare them, they look the same. Well, it's how you measure the efficiency. So down here, what is the efficiency of a heat engine? Eta is equal to what you desire, W cycle out, divided by what you have to supply, Q in. The coefficient of performance, they don't say it's the efficiency, it's coefficient of performance because it's still the ratio of what I want divided by what I have to supply, but it can be greater than 100%. So the coefficient of performance for a refrigeration cycle is what I want. What do you want out of the refrigerator cycle. Do you want to pull a lot out of the cool refrigerator, or do you want to dump a lot of heat into the kitchen? What do you want? I know it's a choice. Or do you want a large electric bill from CPS? You know, the bill from City Public Service Electric Provider. You want a large bill from CPS? No, we don't want that. What do you want? I want a large Q in from the cold, right? But what do I have to provide to make the system work? I have to provide the work of the cycle. Now the heat pump, COP, same coefficient of performance, but the subscript HP to emphasize the heat pump, slightly different than the definition of the coefficient of performance for the refrigeration. What do you think is different? Not the numerator is different, not the denominator. You still have to supply work of the cycle to make it work, but what do you really want? It's winter. Do you want to make the outside of your house colder? Or do you want to make the inside of your house warmer? Inside of the house warmer. That's all. So it's going to be the Q that comes out of the cycle. That's the only difference in the here between the two. All right. Let's do this. I'll scroll down. Might as well cover it right away. The work Q out, we already said that Q out was Q in plus W cycle, true? So what we're going to do is we're going to say that the COP of the heat pump is the Q out, replace that by Q in plus work of the cycle divided by the work of the cycle. That's equal to 1 plus Q in divided by the work of the cycle, true? So there's a strong parallel between the heat pump and refrigeration cycle, and you can see it in the definition of the COPs. So the COP of the heat pump is 1 plus the COP of the refrigeration, because this simply is a COP of the refrigeration. It's just a matter of perspective. What do I really want out of this system? Do I want a large cooling or a large heating? If you want a large heating, you get a COP that's 1 plus the COP for cooling. All right, let's move on. Consider a cycle with the heat transfer in of 60 kilojoules and a network in of 30 kilojoules. Notice this little word right there, in and in, they make a big difference. So we want to sketch it, and we'll put work in of 30 kilojoules and the heat in, Q in, of 60 kilojoules. Can you tell me what the Q out is? What is the Q out of the system? 90. Energy balance around the system operating in a cycle. You got 30 in, 60 in, you have to have 90 out. What's the coefficient of performance if this was a refrigeration? COP refrigeration. Q in over the work, 60 over 30. COP refrigeration's 2. And the last part, COP for the heat pump, you know that's going to be 1 plus that. It'll turn out to be 3. Make sense? Right, press forward. Cycle. Now what we want to do is talk about cycle can be analyzed as a sequence of processes. We don't have a lot of property diagrams at our disposal to visualize a cycle, but the one that we have is a PV diagram. So think about it. Here is my pressure volume diagram. Let's say I start at state 1 right there. I'm just throwing it out. Well, you could put some numbers here. You could put V1 and P1, etc. Maybe this is all in kilopascal. Maybe these are all in meter cubed. But don't get too bogged down in it. But I have to have a cycle. The beginning state, state 1, has to equal the ending state after I go through a sequence of processes. I can have a 2-process cycle, or a 3-process cycle, or a 4-process cycle. Let me just say 3 and 4 process cycles are the norm for this class. So let's go with the 3-process cycle. So let's say I just 1 to 2. Can you describe that process? Is it constant pressure? Is it expansion or compression? Compression. Well, I need to move to another state, state 3. There's a pretty simple process from 2 to 3. I didn't say this is a realistic cycle. I'm just making this cycle up, but that's what we do in thermodynamics, and then we analyze it. But if I want a 3-process cycle, I need to get back at the end of the next process to the initial state. So guess what? So what are the 3 processes? Process 1 to 2, process 2 to 3, and then process 3 back to 1. This state has to match that state or I didn't close it, right? That's almost too obvious. But that would be a 3-process cycle. Did I ask what describes the process from 2 to 3? What is that? Constant volume, pressure increase. What about 3 back to 1? What's happening? Is it expansion? It's expansion and the pressure drops during the expansion process. Let's say somebody else says, I have a different PV. Let's start, I don't know, let's start state 1, the same location. But let's go like this, then back again. So up to 2, then over to 3, then back again. All right. There's a couple things that maybe I'll just say it right up. One of these, what you can do is you can analyze the work for each of these processes. You can analyze the work 1 to 2, the work 2 to 3, the work 3 back to 1 again. True? Let's take a look at this work 1 to 2 for this process over here. Can you just tell me if work 1 to 2 is either positive or negative? For 1 to 2. It's negative. Our sign convention, it's negative because what you're doing is you're compressing the system. It's squeezing the system. So this is going to be negative. What about the work 2 to 3? That one's 0. Why? Yeah, we can do the same thing over here. 1 to 2, work 2 to 3, and then work 3 to 1. We'll do the same thing. But what about 3 to 1? Is it positive, negative, 0? It's positive. Now, here's a question. The magnitude of work 1 to 2, compare that to the magnitude of the work 3 to 1. Is that the right symbols for magnitude? Do you like those? I take the absolute value of the work 1 to 2 and compare its magnitude to the work 3 to 1. Which one is larger? Is it this way, or that way? Which one? 3 to 1 is larger. Why? Why? Because even though the volume change is the same, one was compression, one's expansion, during that volume change, one of the pressures have higher than the other. So what are we doing? We're pushing out, we're expanding at higher pressures than we're compressing. Do you see that? See, it's expanding at relatively higher pressures than it's being compressed at. If the gas or the fluid is expanding at higher pressures than what it's being compressed at, guess what? It's a work-producing cycle. It's a power cycle. The net work out of this cycle is positive. The net work of the cycle, it'll be greater than 0. It'll be a power cycle. Okay, how do I calculate the net work of the cycle? Is the work of the cycle simply the work 1 to 2 plus the work 2 to 3 plus the work 3 back to 1? Yeah, you sum up each of those 3 steps. And if you sum up each of those 3 steps and you have a positive so many kilojoules, you say, oh, for every operation of the cycle, I get that many kilojoules of work out, if it's positive. But take a look at this one. What's the difference? This one's rotating in the general clockwise direction, meaning expanding at high pressures, compressing at low pressures. What about this one? Counterclockwise. So where is it expanding? At relatively low pressures between 3 and 1. Where is it compressing? Relatively high pressures between 2 and 3. So guess what this cycle is? It's not a power cycle. This would be either a refrigeration cycle or a heat pump. They have the same, it's just what do you want? You know, do you want cooling or heating? That's the only difference between those 2 cycles. And guess what the work of the cycle is? The net work of the cycle for this one over here, where it's either refrigerating or heat pump, is going to be negative. I have to supply power to make it work, or energy work to make it work. Does that make sense? All right. For each of these legs of these processes, we can write the first law. And then we can sum it up and analyze the cycle. Let's try this problem. A gas in a piston cylinder assembly operates in a cycle where the states are given. Let's just plot the states. Let me do this. I'm going to pause for a minute to help you a little bit. Pressure in units of kilopascal and volume in units of meter cubed. And I want you to take and find diagram on this PV diagram, state 1, state 2, state 3, where these are the volumes and those are the pressures, okay? Just put them on. And then continue to read the problem and go as far as you can go while I kind of walk around and check on you. So a lot of us went ahead and they said, what's the range of the volumes that I see? Okay, so 1, 2, 3. You could put 4, but a lot of people put 0, 1, 2, 3, right, for meter cube. Then you look at the pressure range. You say, okay, 1, 2, 3, 4, 500 to 400 to 300 to 200 to 100 to 0 kilopascal. I would encourage you to label your axes this type of problem. Then we can easily, with confidence, put in state 1. It's at a volume of 1, pressure of 500. There you go. That's state 1. Then state 2, volume of 3, pressure 300. That's right there. State 2. And then 1, 100, state 3 right there. And the problem said it's straight lines on a PV diagram, so it's just there. Most 99% of the students got that. That's great. Now I want to calculate the work for each process. So I need to calculate the work 1 to 2. So work 2 to 3. And the work 3 back to 1. Before I jump into the math, which ones are going to be negative? Which ones are going to be positive? Are any of them going to be 0? Can I look and see if one of them's 0? Which one's 0? So right away, and you could put kilojoule. Professor, is this one of the times where I don't even need to put units? You know what? This is one of those times you don't even need to put a unit. Because 0 kilojoules is the same as 0 BTUs, right? It's like, that's a case where you don't need any units. But if you wanted to put kilojoules, would that be wrong? No, that wouldn't be wrong. All right, now, how about work 1 to 2? Is it positive, negative? It's positive. Now, how many people have calculated work 1 to 2? Only that many hands? Let me give you calculate work 1 to 2. Don't watch me do it. You do it. You calculate work 1 to 2. All right, so yes, you can analytically get P as a function of V, and then come down and do the work is the integral of P dV, and maybe this P is equal to Y is equal to mx plus B, some slope mx plus B, or mv times V and integrate dV. And I see a number of people doing that, and that's fine. That's exactly the way I tried it when I was in your shoes. I'm all right out of a math class. I can do it analytically. But what's the beauty of this here diagram? Somebody says, I want you to calculate the integral of f dx from x1 to x2, and there's the function f. It's the area under the integral. Somebody says, I have a straight line. Can you calculate the area under that straight line? Pretty easy, isn't it? So what's the area under that? Well, let's see. It starts at 500, ends at 300. What's the average? 400. It goes from 1 to 3. I think that's a change of 2. We can do that one in our head. So we have 400 kilopascal average pressure over a volume change of 2 meter cubed. And then some of you, that's good that you're asking the question now, because you don't want to stumble on the exam, right? You got to know how to convert units. And somebody says, is kilopascal times a meter cubed, is that a kilojoule? Yeah. And what you can do is start, this is the way I do those things when I'm in doubt, insert new page, is I say meter cubed times a kilopascal is equal to a meter cubed times a kilopascal. Did I write the equation correct, or did I make an error? Isn't that correct? And then I multiply by, okay, a pascal is a Newton per meter squared, true or false? So I can get rid of the pascal, and I can get rid of 2 of the meter squared, or the meter squared, and then I'm going to multiply by joule is a Newton meter, true or false? Newtons go. The last meter goes. What am I left with? Kilojoule. So 1 meter cubed times kilopascal is precisely 1 kilojoule. It's something to watch me do it. Say, I'll commit that to memory. Don't do that. Own it, right? Know how to rederive it. Envision yourself studying with somebody and they say, no, you're wrong. I'm right. No, you're wrong. I'm right. Blah, blah, blah. And then you just prove it. I'm going to show it to you. This is logical. This works. It's not like my equation sheet said it, or even worse, my professor said it. That's even worse, because the professor is wrong half the time, right? Didn't you see how many errors I make in any lecture? So anyway, make sure that you can do that, and now you have it. So what do we have? 800. So the work 1 to 2 is 800 kilojoules, true. What about the work 2 to 3? We knew it was negative because it's being compressed, but it's the area under the curve, the same type of logic, and you find negative 400 kilojoules. What's the work of the cycle? Sum up the work for each of the processes, and you get the work of the cycle equal to 400 kilojoules. What about the net heat transfer? No, is this a power cycle, right? Is this a power cycle, yes or no? Yes. What about the thermal efficiency? You can't solve it. You got to go to the next slide. But I anticipated some people would run ahead and others would be trying to struggle with earlier concepts. And then they hit this, they'd chew on that for a while because they're stuck. You can't calculate the thermal efficiency unless you know how much heat is being brought into the cycle. You now know what is the net work out of the cycle, 400 kilojoules, but I don't know the heat in. True? Here's more information. They give us the same states, but they say for process 1 to 2, the change in U, what is the name of U? I forgot. Internal energy. The change in internal energy is 650 kilojoules. And for the process 3 to 1, Q 3 to 1 is 1,000 kilojoules. So We already determined the work for each of those. The net work for the cycle. Now, what is the net heat transfer for the cycle? There's the answer, but let's calculate it. What are they asking me to calculate? For this part C, what are they asking me to calculate, part C? Q cycle, or sometimes the right Q net of the cycle, something like that. But what is it? Is it equal to Q1 to 2 plus Q2 to 3 plus Q3 to 1? Is that what it's equal to? It sure is. But it's something else that it's also equal to. Let me do this. Let me write down the first law for each of the three processes over here. We'll have it the energy at state 2 minus the energy at state 1. Q in from 1 to 2 minus the work out from 1 to 2. Let's write it for the process 2 to 3. E3 minus E2 equal to Q2 to 3 minus work 2 to 3. And let's write the first law for the process 3 to 1. E1, the final state, minus E3, the initial state, equal to Q 3 to 1 minus work 3 to 1. This always challenges me, the subscript notation on it. It's easy when I go 1 to 2. Oh, start at 1, end at 2. But when I go 3 back to 1, I have to start at 3 and end at 1. Did I get the subscripts right on that last process? Does it make sense? I have equation 1, equation 2, equation 3. Guess what you do? You sum them up. If I sum up everything, what do I get on the left-hand side of the equal sign? Can you see that this E1 and that E1 cancel? That this E2 and that E2 cancel? That E3 and that E3 cancel? So the change in the energy around the cycle is equal to 0. And then you think about it for a minute. That's how much energy I've stored in the system. If for every cycle somehow it wasn't 0, then I would either go up, 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 or down, 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 depending if it's positive or negative, but it's 0, hence that makes sense. I'm just going in a cycle, and the net energy stored in the system doesn't increase or decrease after every cycle. It may go up a little bit for the first process, may go down for the second process, may do something on the third process, but the sum of them all are 0. Okay. What about over here? Well, that's going to be the sum Q1 to 2 plus Q2 to 3 plus Q3 to 1. Then you have minus W1 to 2 plus W2 to 3 plus W3 to 1. And now 0 is equal to Q of the cycle. That's the sum of all the Q's over all the processes into the cycle minus W of the cycle. So another way to calculate Q of the cycle is what? It's precisely equal to the work. The net amount of heat into the cycle, over the cycle, is equal to the net work out. So how do I calculate part C? Don't go this route, go this route. And part B had the answer, so it's just the same numeric value, 400 kilojoules. Does that make sense for the answer for part C? Now, part D. That's D, sorry. What is the heat transfer for each process? So what is Q1 to 2? What is Q2 to 3? And what is Q3 to 1? Well, take a look. What information did they give us in the problem statement? That's always nice. They give you some information in the problem statement and ask you exactly the same information back. So for Q3 to 1, it's 1,000 kilojoules, boom. So I have an equation where I know this one, I know that one, I don't know Q1 to 2, and I don't know Q2 to 3. What am I going to do? Focus on one of the processes where they give me the internal energy change. So if I go back up here and write it for process 1 to 2, And here I'm going to neglect changes in kinetic and potential energy. Hence, the change in the total energy is simply the change in the internal energy. So it's U2 minus U1. That information they gave us, didn't they? They gave us this, I'm kind of writing backwards here, is 650 kilojoules. Q 1 to 2 is what I'm looking for. What's the work 1 to 2? Did we calculate the work 1 to 2 before? It's positive 800 kilojoule. Is it important that I have this negative sign right there? Yeah. And so Q1 to 2 is 800 plus 650. It's a pile. It's 1450 kilojoules. Make sense? All right. What about the heat transfer Q2 to 3? Go back to this equation because you just solved for that. And now Q2 to 3 is Q cycle minus Q1 to 2 minus Q3 to 1. And you find it's negative 2050 kilojoules. Now we can finally calculate the cycle thermal efficiency. What is it? It's going to be the work net of the cycle. Here. Work of the cycle divided by Q of the cycle. True or false? Is the thermal efficiency work of the cycle divided by Q of the cycle? It's only Qn. Remember our illustration? We had some heat in, we had to throw some heat out of our heat engine. So it's not, this is a common error. This just needs to be only the in, Q in, right there. All right, so I look back. In the process 1 to 2, is that a Q in or an out? It's an in at 1450. How about 2 to 3? Because of the negative sign, it's an out. And then from 3 to 1, is it an in or an out? It's an in. So Q in is the sum of Q1 to 2. Let me write it like this. Q1 to 2 plus Q3 to 1. So this is the work of the cycle out. So the work net of the cycle is 400 kilojoules divided by 2450 kilojoules. If you have a calculator, can you check that at 16.3%? It is. Does that look good? All right. Oh, no. Yep, that's this type of class. The problems only get worse. Doesn't it look like I don't want to even try this problem. It looks so complicated. But let's see how far we can go. Gas undergoes a cycle in a piston cylinder assembly consisting of how many processes? 3. Process 1 to 2 is constant pressure. They give us P of 1 bar. V1, 0.025 meter cubed. And the work 1 to 2 is a positive 1.5 kilojoules. Right away, just pause for a minute. Can you kind of sketch a PV diagram and start to put any information down? Like, what does the process 1 to 2 look like? All right, what I'm going to do is, I'm really serious about this. I know I only have about 10, 20 minutes left. I'm going to pause.